Good. I think we can start. Thanks, everyone, for joining this new edition of the uh, Cambridge Ellis Unit Seminar Series. First, I would like to thank the sponsors of the Ellis Unit. We are really thankful for their support. And today we have Andrew Gordon Wilson, who is currently a professor in the Courant Institute for Mathematical Sciences and Center for Data Science at New York University. Andrew is well known here in Cambridge. He received his PhD from the University of Cambridge. He studied here, working with Subin Garamani, with Carl Rasmussen, and many others in the Cambridge Machine Learning Group. He studied a Bachelor of Science in Mathematics and Physics from the University of British Columbia. And prior to joining NYU, he was a professor at Cornell, a postdoc at CMU. And his research work is focused on developing a foundation for building intelligent systems. He has been expo chair, tutorial chair, workshop chair, senior area chair, and many conferences in machine learning. Has received many awards, including the NSF Career Award, Amazon Research Award, Best Paper Awards, Best Reviewer, Area Chair, and even Best Dissertation Award. And yeah, today he's going to talk about machine learning is linear algebra. And I'm going to stop sharing my slides. And Andrew, we are ready. So you can start sharing your slides.
Thanks so much, Miguel. It's a great pleasure to be here. Thanks for the invitation. So as Miguel said, I'm going to be talking about how machine learning is really just linear algebra. And in some sense, this is actually a research journey that started when I was a PhD student at Cambridge more than a decade ago. And it's evolved a lot since then. And some of the focus of this talk will be applying this perspective to make efficient transformers. But it's a research agenda which is actually quite broad and expands a lot beyond that as well. And we'll be discussing some of that broader context at the beginning of the talk. About half of the talk will be about work that's maybe 2 months old. And then near the end of the talk, I'll be talking about work as well that's about 2 weeks old, but fits into this bigger picture. Okay. Also, yeah, it's great to be here virtually in Cambridge. I'll also be in person likely in the summer. So if you're around, I'd always be happy to catch up and chat. So to start thinking about this perspective of machine learning as linear algebra, it's instructive to consider a well-known example where we can go from a multi-layer perceptron, a fully connected neural network, to a convolutional layer by removing a lot of connections and then enforcing parameter sharing across some of the remaining connections. So the connections in purple all have the same value and green all have the same value. And this reflects our assumptions of translation equivariance, so wanting the labels, for example, of our images to be essentially invariant to translations of those images, as well as a locality bias, say nearby pixels being more correlated than far away pixels. And algebraically, what's happening is we're replacing a dense matrix multiplication with a matrix W in the MLP with a multiplication with a convolutional matrix, which is sparse and has parameter sharing. And so once we have that sparsity and that parameter sharing, we can get enormous computational savings. And it might be useful actually to consider a simple example of this. And I might ask some questions throughout the talk, so don't be shy. Feel free to unmute and answer. So if we had a 1000 by 1000 pixel image, and we were modeling this image, say trying to classify it with an MLP with a single hidden layer, and it had just 1000 units in its hidden layer, how many parameters would that model have? So I'll just repeat this again if you're still parsing the question. So we have a 1000 by 1000 pixel image. Each pixel is an input dimension. We have 1000 hidden units, but a single hidden layer, and it's densely connected. It's an MLP. How many connections do we have in that model? Can anyone tell me?
It's 1 billion.
Exactly, yeah. It's not a trick question. So we have a million input dimensions and 1000 hidden units, and 1000 times a million is a billion. So we have actually a huge number of parameters already and not a particularly powerful model. Like that's not actually going to do a very good job of image recognition. And so by moving to convolutional layers, we gain an enormous amount of computational efficiency in some sense. We can build much deeper networks, which will be able to discover much richer representations, but for the same computational budget as this other model, which is actually not going to be very effective in practice. And so one question that we're going to be considering throughout this talk is how we can really systematize this process of finding structured layers. What's the science behind proposing different types of structures when we're designing these architectures that will particularly lead to the best compute optimal efficiency, meaning that for a particular computational budget, we'll get the best possible performance. And so in some sense, it might feel like machine learning is moving in the opposite direction. Like we've gone from handcrafted feature engineering to particular architectures for particular domains, like convolutional neural nets for images, recurrent neural nets for sequences, MLPs for tabular data regression, et cetera, to transformers for seemingly everything. However, machine learning really just means learning from example. It's inductive learning, and we cannot do induction without making assumptions. So we really aren't moving away from assumptions, despite what it might look like. Perhaps our assumptions are a little bit less transparent than they used to be, but we still have assumptions. And we really need to think critically about what those assumptions should be. Perhaps some assumptions are going to be more universal than others in the real world, and how we can most effectively represent those assumptions. And so really, we're going to be considering this chain where we start with our assumptions, we understand how those assumptions manifest as algebraic structure, and then we consider how we can algorithmically exploit that structure for computational efficiency. And so this journey, as I mentioned, really started near the beginning of my PhD when I was working on Gaussian processes. So Gaussian processes involve needing to solve a linear system with some n by n covariance matrix and other operations with that matrix like log determinants and derivatives, etc. And so naively, this means that using a Gaussian process will incur n cubed complexity if you have n training data points. So even though these are really beautiful models, which are really philosophically well motivated, it was quite frustrating because it meant we couldn't really apply them to that many problems because of these computational constraints. And so one thing that I sort of spent a lot of time reflecting on was how our modeling assumptions, for example, our choice of covariance function, might influence the structure of those covariance matrices, and then how in turn we could exploit that algebraic structure to improve the computational complexity of these operations. And this was just kind of a watershed moment for me because the n cubed complexity wasn't really necessary. Like there was a lot of structure in these matrices already that was just being ignored. So it wasn't really the case that we needed to impose additional assumptions in order to achieve computational scalability. We could actually just exploit the assumptions that we were already making, but kind of ignoring. So it wasn't really like a free lunch. It was just we were paying too much for lunch and we needed to start paying the right amount. And this observation really carries over quite broadly. So quite often our modeling assumptions will manifest in some way as algebraic structure. I wasn't so sure about that actually when I was working on Gaussian processes, and I was kind of worried about it. Like, to what extent does this generalize to other models, other problem settings? But it turns out that it really is quite generic. So in normalizing flows, we need to compute log determinants efficiently. When we're using neural nets to model PDEs, we also end up with poorly conditioned linear systems where matrix structure meaningfully reflects our modeling assumptions. Second order optimizers, so we need to compute, say, a Hessian or a Fisher matrix, and that's often quite computationally intractable, and so it's not uncommon to have some efficient representation of those matrices, say like a diagonal or low rank, but there's also a science behind how to do that well. We already saw this example with convolutional neural nets. It also shows up in optimal transport and in really many, many other places. So let's return to this convolutional neural network example and think about it in a little bit more detail. And so I said, when we have these assumptions of translation, equivariance, and locality, we're replacing a dense matrix with a Toeplitz matrix. And a Toeplitz matrix just means that you have constant diagonals. And so in the top left, I have sort of an example of what a convolution matrix will look like. In the right panel, I have an example of a symmetric, just a generic symmetric Toeplitz matrix. And so time for another question. If we wanted to represent the matrix on the right in memory, it's a D by D matrix, how much memory would we actually need?
People can write in the chat if they want.
Yeah. Yeah. So if we wanted, how much memory does it take to store the matrix on the right in the top? It's 3p, so it's D. I guess the P is for the left one. So it's a D by D matrix. D squared, naively it would be D squared, but we can do better. OD. Yeah, that's right. So if we just look at the structure there, we can see that all of the information in this matrix is contained in its first column. And so already just that trivial observation leads to enormous computational savings, right? Like it's hard to even represent matrices bigger than say 50,000 rows and columns if we're not sort of understanding that those matrices might have some kind of special structure. So now we can go from 50,000 by 50,000 to like well over 1,000,000 by 1,000,000 just by recognizing that because of this structure, we can store this matrix in OD memory instead of OD squared memory. We can also embed these kinds of matrices into what are called circulant matrices and get very fast matrix multiplications using fast Fourier transforms operating just on the first columns of these matrices. And this will lead to n log n matrix multiplies instead of n squared. And then those fast matrix multiplication routines can be used as part of iterative methods like linear conjugate gradients to efficiently solve linear systems, etc. And so this structure also arises quite naturally in a lot of settings. So if we're using, say, a Gaussian process with a translation invariant kernel, and most kernels are translation invariant, like the RBF kernel, Mathieurin kernel, rational quadratic, etc. And it's to a one-dimensional input space that's regularly spaced, like a time series, for example, then we'll get a Toeplitz matrix. We also see this show up if we have some sort of other sort of translation invariant assumptions in other settings, like image recognition, where we got like convolutional structure. Okay. Another really instructive structure to consider is the Kronecker product. So this is used a lot in itself, but it's also used as a building block for other useful matrix structures. So a Kronecker product of two matrices A and B is such that we take every entry of A and multiply it by the whole matrix B. And so if I have a Kronecker product of two 1,000 by 1,000 matrices, what will be the dimension of the resulting matrix? This is another question.
People can write in the chat again.
So we have a Kronecker product of two 1,000 by 1,000 matrices. What's the dimension of the resulting matrix? A million by a million. So this allows us to decompose enormous matrices into much, much smaller matrices. And then we can do operations on those much smaller matrices to derive properties of the really large matrix. For example, we can separately do eigendecompositions of the small matrices within this Kronecker product in order to get the eigenvalues and eigenvectors of the really big matrix. And so this quite often means that we can work with problems that have millions of points if we're thinking about this from the perspective of Gaussian processes and a Kronecker decomposition of the covariance matrix at the computational cost of working with, say, just a couple thousand points. So to give a very concrete example, we could return to this image question I posed when we were thinking about convolutional structure, where we have a 1,000 by 1,000 dimension image. In this case, we can imagine each pixel is a data point, and maybe we're doing regression. So it's like a two-dimensional problem, and maybe we're doing in-painting or something like this. We'll get a million by a million covariance matrix. So we won't even be able to store that on a computer unless you're unless you're Elon Musk or something. Even then, I'm not sure. We'll see if we use many popular covariance functions like the RBF covariance function, that this covariance matrix will decompose as a Kronecker product of two 1,000 by 1,000 matrices formed by applying the kernel associated with kind of each dimension separately to the 1,000 pixels in the horizontal axis and the 1,000 pixels in the vertical axis. And so basically that means that we can solve linear systems, compute eigenvalues, and so on at roughly the computational cost of working with 2 times a 1000 by 1000 matrix, which is just really incredible because that means we can get answers in seconds that otherwise would have taken our lifetime to compute. But we're not making any additional assumptions. We're just exploiting assumptions that people are already making. And so this kind of Kronecker structure arises quite naturally when the input is a set of objects of the same kind, nodes in a graph, points on a grid, patches of an image, words in a sentence. It's also quite often imposed to approximately perform operations with large matrices so that we can operate on much smaller matrices. So it arises as a consequence of our assumptions, but it's also a popular additional assumption itself. And I'm going to ask another question. So can you give me an example of where Kronecker factorization is assumed in optimization, a second order optimization that assumes a Kronecker factorization? We could say a Kronecker factorized optimization procedure. Okay, so the method I had in mind was proposed around 2015, so maybe that's too old for this crowd. It's called KFAC. It's a natural gradient descent method where you have this empirical Fisher matrix and a Kronecker factorization is assumed for computational tractability. Kronecker factorizations are often assumed as a more expressive but still efficient way of representing large matrices than say low rank structure or diagonal or block diagonal, etc. So like if you have some bottleneck associated with some big matrix operation and you feel like diagonal or low rank is too severe of an assumption, then a Kronecker factorization is actually quite popular because you have a full rank representation and it's relatively expressive. It also shows up, you've probably heard of the shampoo optimizer. We see a Kronecker factorization of the preconditioner in the shampoo optimization procedure. And actually, as a incidental aside, it's quite interesting that some of these second order optimizers are starting to now overtake standard optimization procedures like ADAM and SGD and deep learning. So there was a lot of frustration, I think, for quite a while around the fact that SGD and ADAM reigned supreme despite all sorts of better ideas for doing optimization. So deep learning was really rejuvenated in 2012 with the AlexNet ImageNet result. And there was an effort, I think, from 2012 to 2015 to propose better stochastic optimizers than SGD. And this led to AdaGrad and ADAM, which I'm sure many of you have used. And after ADAM, there were many, many optimization methods that were proposed, many hundreds that were published at NeurIPS and ICML, but none of them really ended up becoming like a standard procedure that we used. And there was actually an interesting paper written about this by Philip Hennig and his group called Descending Through a Crowded Valley. And my takeaway from that paper was, well, we've proposed all these optimization procedures, but really, ADAM W is basically the most practical thing to do in most cases, and it doesn't have that many free parameters that we need to fiddle with, etc. And so it was a bit sort of depressing in some sense. Like it felt like, okay, we're just stuck with these methods forever. But then out of the blue, about 2 years ago, we started to see second order methods and second order inspired methods like shampoo, distributed shampoo, muon, soap, convincingly overtake ADAM in training, especially large models. And so I think in the Gemini effort, their tech report sort of vaguely alludes to using a second order optimizer, which I very much suspect is distributed shampoo. These are kind of newer procedures that are actually being used in production at a very large scale. And so I think that's a very exciting development, and we might touch on that briefly at the end of the talk. Okay, so I said Kronecker matrices are useful in themselves, but they're also useful as a building block for other structure. And so when you look into the mechanics of how you multiply a Kronecker factorized matrix, you end up doing some reshaping such that you're multiplying against a block diagonal matrix where the parameters in the blocks are all shared. There's a newer type of structure called monarch structure, which relaxes that parameter sharing assumption. And this has actually led to pretty good compute optimal scaling relative to dense layers in some settings, and I'll return to that, of course, a bit later. There's also tensor train structure, and it's complicated to talk about tensor trains in full generality, but a tensor train matrix is exactly equivalent to a sum over R Kronecker product matrices, where R is said to be the rank of the tensor train matrix. And for R equals D, the tensor train can represent any dense matrix. So this is going to be a full rank matrix, but you can do efficient multiplies with this matrix. It shows up in a variety of settings. It's natural for modeling systems that decompose into subsystems with pairwise interactions like quantum spin chains, hidden Markov models. It's also the first example that I'm aware of where people have imposed structure on MLP layers very successfully. So there was a paper in 2015 called Tensorizing Neural Networks, and uh, it basically takes convolutional neural nets mostly and the fully connected later layers, which were common at that time in those networks, and replaces the dense linear layers with tensor train structure and finds that you get big computational savings and still retain pretty good performance. And so this paper actually was very impactful. I think it's cited more than 1,000 times, which is particularly interesting given that in 2015, not many people were really using MLPs. And I think perhaps that's why that research effort sort of vanished for a while. We just moved to really embracing fully convolutional structures. So it became less and less common even for people to have fully connected layers at the end of convolutional neural nets, and people just had really deep res nets. But of course, now with transformers, we're actually using MLPs really quite a lot. And more broadly, MLPs have been making a big comeback. Okay, so in terms of a vision for how to exploit this algebraic structure quite systematically across a number of different problems, it's useful to make an analogy with automatic differentiation. And so automatic differentiation has really had an enormous impact. And in some sense, it feels trivial, but it took a very long time for it to become mainstream. So when I was in my PhD at Cambridge in 2010, say, it was very common for people to just manually derive derivatives. Like I went through that pain to some extent, but not nearly to the same extent as some of my lab mates who had appendices in their PhD theses that were like 100+ pages of computing derivatives. And in some sense, that was sort of a signal for me about what I shouldn't work on because I just wouldn't have the patience to do those kinds of manual derivations. Interestingly, in the last 10 years or so, automatic differentiation has been very mainstream. And in order for that to be possible, we really needed to develop the right base case primitives, the right software abstractions, computational graphs, etc., the right modifiable compositional rules, and frameworks like PyTorch and so on that implemented AutoGrad very effectively. And so I think that structure-aware linear algebra is similarly ripe for automation. Like there's just a lot that we can do under the hood that will allow us to focus again on prototyping ideas instead of implementation. So to that end, we've been developing this framework called COLA, which stands for Compositional Linear Algebra. Essentially, what COLA does is it represents matrices as a linear operator abstraction. So it doesn't represent a matrix explicitly, it's just this linear operator representation. And you can endow that linear operator with anything that you know about the matrix. Is it low rank? Is it Kronecker? Is it sparse? Is it adjoint, etc.? And then you can add and multiply linear operators together and get other linear operators. And when the user then wants to do some kind of matrix operation, this framework will recursively exploit compositional structure to propose a numerically efficient algorithm. And it will also account for the hardware that's available to you. So if you have access to GPUs, for instance, iterative methods become very compelling, like linear conjugate gradients, because they're very easy to parallelize. And GPUs are very good at parallelizing things like that. And so in some sense, that's this part of the story behind why deep learning became so successful. And so I think more broadly, even if we're not using deep neural networks, we should be embracing algorithms that can effectively exploit our hardware. And so COLA is partly intended to help people do that easily, but it also has this linear operator abstraction combined with multiple dispatch inspired by Julia in order to automatically propose all sorts of efficient numerical algorithms if you're considering a variety of different structures. And so what this allows you to do, I think, is like if you have some structure already that you know you want to use, like you're using some Kronecker factored Laplace approximation or some second order optimizer that has like a particular structure being used to represent a Hessian and so on. You can just kind of efficiently exploit that structure with the algorithms that are in this library if you have access to a GPU. And you can have access to all sorts of really good iterative methods. So not just conjugate gradients, but also stochastic Lanczos quadrature, minres, etc. And then you can also just prototype. If you don't know what structure might be a good representation for your problem, you can try out all sorts of structures quite easily, over the course of a day instead of over the course of years, and get a sense of what structures and what corresponding assumptions might make sense for this problem that you're considering. And I think this, really could be sort of a watershed effort in the sense that this sort of quickly enables us now to test all sorts of ideas which would have otherwise just been out of reach. Quite similarly to how AutoGrad has kind of enabled us to prototype all sorts of ideas that we just couldn't have really tried because it would have meant computing 100 pages of derivatives by hand, and no one really can do that more than once, I think, in this lifetime. Okay, so we've been talking about these principles quite generally. We're now going to be considering how to apply them to transformers. As I mentioned, transformers really are a composition of multi-layer perceptrons and something called attention. You end up doing a lot of dense matrix multiplications when you pre-train a transformer and when you use it at inference time. I apologize to the Bayesians. I am sort of a Bayesian myself, so I'll say test time from now on. And this is really the big computational bottleneck. So people have focused a lot on efficient attention, like how do we go from quadratic attention to linear attention, et cetera. But I think at this point with flash attention and so on, really there is a lot more mileage in trying to understand how we can make the MLPs efficient and how can we do that really systematically. And so this talk is largely about 3 papers, especially the last one, searching for efficient linear layers over a continuous space of structured matrices. So I said we're going to consider this from the perspective of compute optimal efficiency, meaning that for a given computational budget, we want the best possible performance. It's been observed that neural nets and in fact other models follow pretty well-behaved scaling laws empirically, which has been quite surprising. And so I here have a visualization of what are called the chinchilla scaling laws, where you find sort of like the right network size and the right data set size in order to achieve optimal performance for a given amount of compute. And these data points here are all described by a curve, which can be expressed in terms of a coefficient b and a scaling exponent a. And very significantly, if we can think of better ways to represent these linear layers in transformers, we can modify this scaling exponent a. And what that means is then we can get exponential increases in performance with increases in computation. And so that could really make a profound impact in practice. Just to kind of summarize some of the things that we've been talking about so far and provide some context for the next slides, we'll be considering quite a variety of different structures. So we've talked about dense structure, low rank, convolution, Kronecker. We briefly mentioned monarch is what you get if you remove the parameter sharing in this block diagonal matrix when you multiply a Kronecker matrix. Tensor train is a sum of Kronecker matrices. We're going to propose a new structure called a block tensor train based on some of the principles that emerged when we try to understand how we want to approach this search. And I've also listed the assumptions that typically correspond to these structures in several example applications. Here we're imagining we have a D by D matrix. I have the computation required for doing a matrix multiply with these matrices. So dense matrix is say D squared and the number of distinct parameters associated with each of these matrix structures. So we'll actually be considering a special sort of formulation that includes all of these structures as special cases in a moment. But first, we need to understand how we should approach replacing these layers with various different structures from an engineering perspective. So if we just try to do this out of the box, like I take an MLP and then replace all of its layers with low rank matrices, you'll find that it just doesn't work. Like you just get terrible performance. And I imagine a number of people have just stopped there. I mean, we almost stopped there. Like it was kind of very sad and it was kind of unclear why, none of these structures were actually leading to anything interesting. And it turns out that good initialization is absolutely crucial, as well as like reasonable learning rates. And even if we use ideas like maximal update parameterization, referred to as mu-p, things still sort of break. So what I've listed as naive here in these pictures corresponds to standard mu-p. And so mu-p actually is a very inspiring, I think, success story of theory in deep learning. So there's this question of like how relevant theory should actually be in modern deep learning. I think it's very relevant and it's a very exciting thing to work on right now. And I'll talk about that a bit more later. But like one of the big concrete examples, I think, of theory leading practice is mu-p. So mu-p was derived from these infinite limit analogies. So you may have seen this result that like an infinitely wide neural network, Bayesian neural network, converges to a Gaussian process with a particular covariance function. This was derived by Radford Neal in the mid-1990s. And then since then, there have been derivations for multi-layer networks, et cetera, and there's related work on neural tangent kernels and so on. Mu-p basically pursues these infinite limits to try to understand how we should consider initializations and learning rates as we like increase, for example, layer width. And so this is actually used in production by all sorts of big companies, expending millions, maybe billions of dollars training these big language models. Unfortunately, it did not work for us out of the box because we're not using dense matrices, we're using structured matrices. And there's a lot of detail that came into trying to figure out how to generalize mu-p so that it would be structure aware, but the high level story is we ended up representing structure matrices as compositions of smaller dense matrices and fixed norm-preserving linear transformations. And this allowed us to kind of decompose the problem by applying the same spectral considerations that were used in mu-p to each dense component separately, treating each structured layer as a deep linear network. And so in the Compute Better Spent paper, we go into a lot of the detail behind that. And once we had that structure-aware mu-p initialization, we started to see very exciting results. So I guess in the panel A here, we see that we get sort of stability when we look at the RMS of like the last layer as we change width. We also see that on the right panel that we get some quite good sort of learning rates when we follow this procedure. Okay, so now that we've figured out how we can set up the low-level details to properly explore different structures, there's this question of like what space of structures we should actually be exploring. And we proposed this Einsum formulation, which actually contains all the structures that we've talked about so far as special cases, as well as many novel structures. When you start talking about tensors, there's a lot of notational overhead, and I'm going to try to reduce that as much as possible. So in the top of this slide, we have this visualization, which shows how different parameters in this Einsum, there are 7 continuous parameters that define this Einsum, correspond to well-known structures, and the scaling laws for GPT-2 associated with each of these structures. So in green, we just have some generic Einsum structure that we've sampled uniformly from this distribution over these continuous hyperparameters, and we see that it has some sort of intermediate scaling behavior relative to some of these other structures. Part of the reason that we chose Einsums is because they're very general, so they contain all the structures we've discussed, but they also are quite amenable to existing hardware acceleration. So the hope is that you don't need to do a lot of really low-level implementation around parallelization, et cetera, in order to realize some gains associated with any Einsum structure. We additionally introduced a taxonomy over matrices described by Einsum structure, controlled by a few more interpretable parameters. So a rank exponent, which controls the rank of the structures that we're considering, a compute intensity exponent, nu, which controls how expensive it is to do a multiplication with this matrix, and a parameter sharing exponent, rho, which tells us, to what extent we're doing parameter sharing with a particular structure. So the larger rho is, the more parameter sharing we have. And so here we visualize this in the right with this plane where, for example, in the blue plane, we have no parameter sharing. Omega is 0. We see the different colored dots corresponding to the different structures that we've enumerated on the left side of this figure. Okay. So equipped with this taxonomy over the different parameters that will interpretively control the properties of these matrices, we did a number of experiments, and the findings were quite surprising to me. So one of the most significant findings was that parameter sharing often leads to worse scaling. So if we just look at the top left panel here, as omega gets larger, so as the colors get darker, we get more and more parameter sharing, but we can see that the scaling behavior, it gets a lot worse. And so it seems that parameter sharing is actually a really bad idea if you want the best compute optimal performance. And that's surprising because of, for example, the success of, say, convolutional layers in image recognition. Part of the way to resolve this kind of seeming discrepancy with perhaps what we've observed historically in practice is when we're thinking about compute optimal efficiency, especially with larger models, we're not necessarily even training these models to convergence, right? Like they're very undertrained. And so quite often what we really want to do is just like figure out how to decrease our training loss as effectively as possible for a certain amount of computation, a certain input number of flops. And it seems like parameter sharing actually really does not help us in doing that effectively. We want basically as few parameters as possible per flop. Or we don't want to learn fewer than one parameter per flop, sorry. Okay, so among the structures without parameter sharing in the middle panel, we found that full rank structures also tend to scale much better than low rank structures. And the intuition behind that is that low rank structures tend to provide a bottleneck that prevent linear layers from accessing all the feature dimensions. And this also makes it harder to decrease our training loss as efficiently as possible for a given amount of computation. If we consider structures that avoid parameter sharing and are full rank, they have relatively similar scaling laws. And so here we're considering GPT-2, but these results generalize to a variety of other settings, including vision transformers. And so the results kind of suggest that we want full rank matrices. We want to avoid parameter sharing, and like, dense matrices have those properties. So like, is dense really as good as we can do? That's what we're already using. And in order to explore that question, we considered proposing a new type of structure, which is full rank and avoids parameter sharing, but you can also do very efficient matrix multiplies. This is called the block tensor train structure. And in some sense, it's analogous to how researchers derive the monarch structure from the Kronecker structure. So monarch is derived from removing the parameter sharing across blocks in Kronecker structure. Tensor trains are derived from taking sums of Kronecker matrices. The block tensor train is derived by removing the parameter sharing across the blocks of the individual matrices inside the tensor train. Okay, and so when we replace the dense linear layers with this block tensor train structure, we see significantly better scaling behavior. Here we're looking at MLPs and vision transformers. In a moment, we'll also look at these results for large language model.
Andrew, one quick question just to refresh my memory. The block tensor train was the sum of Kronecker products, is that right? Or could you
yes,
clarify
so
a
you
bit?
can exactly. So the block tensor train is a sum of Kronecker matrices, except the Kronecker matrices have been modified so that they don't have parameter sharing across the blocks. The tensor train is just a regular sum of Kronecker matrices.
Okay.
And if it's a tensor train matrix, yeah.
Good, thanks.
Yeah, and so actually it's interesting to note, looking at these plots, that tensor train in yellow is actually one of the worst performing structures in terms of compute optimal scaling, but block tensor train is one of the best. And so the big difference between tensor train and block tensor training is we remove parameter sharing. And so that actually, really just had a big effect on the scaling behavior and enabled BTT to work pretty well, relative even to dense, which is actually fairly competitive, but not as good as the block tensor train. We also have Monarch here, which removes parameter sharing, but it doesn't have this sum of Kronecker or kind of modified Kronecker matrices, so it's less expressive. And expressiveness is actually very helpful in achieving good compute optimal scaling. There was this question I mentioned of like, well, dense has these properties we're selecting for, so why should BTT be better than dense? The reason is that it allows still faster multiplications, and this allows for a given computational budget for us to use networks with wider layers. And networks with wider layers, for a variety of reasons, are much easier to train and discover good representations for. And so I have a figure just showing that on the top left here, where we move from a dense structure to a block tensor train structure. But we have a much wider layer, and we have basically the same computation associated with that wider layer as if we were to use the dense structure. And so that's kind of the intuition behind why that's helpful as well. Okay, so this helped a fair bit for vision transformers. It helped somewhat for large language models. So in the bottom figure here, we have GPT-2 with and without this sort of language modeling head. So on the left, with the language modeling head, the BTT is clearly better than dense. Without it, they're pretty close. Uh, and since uh, bigger models beyond GPT-2 tend to have a relatively smaller language modeling head compared to the other parameters in the architecture, I would expect these gains to sort of start to diminish as we consider larger and larger language models. So the results with VITs are actually really exciting. I would say the results with LLMs are promising, but it's a little bit hard to conclude, that much about their practical significance. So the question is, can we push these results even further? And so one of the big principles that emerged from this investigation was that we want as many possible parameters per flop. And so we might want to consider whether it's possible to have even more than one parameter per flop. And so we could start with something like a sparse mixture of experts layers. So sparse mixtures of experts typically consider like a gated sum of fully connected neural nets. So these are just MLPs, but I'm calling them FFNs here. And this gating function is sparse. So it's usually formed just from a dense linear layer passed through a softmax. And then maybe you just take the top two softmax entries, and those are your weights on like two of the neural networks in this sum of E networks. And so what this means is if you have E experts in your model, you're increasing the number of parameters by a factor of E. But if only K experts are active, the total computation for this number of parameters is multiplied by K over E relative to a non-mixture of experts model that would have this number of parameters. So it's kind of a way of significantly increasing the number of parameters you have without significantly increasing the amount of computation that you're expending. And so in order to push this even further, we decided to not just do a mixture of experts over whole MLPs, but actually have a mixture of experts over individual layers within the MLPs. And we are representing the individual layers, remember, as sums of these modified Kronecker matrices. And so we could have a gating function actually acting over the rank index of this sum. And so this allows for a significantly more expressive mixture of experts that can consider much finer grained routing decisions across the experts. So there are many more possible combinations of experts in sort of an M-layer model using this structured block tensor train mixture of experts than what we would normally have in a sparse mixtures of experts setup. And I think this is where we saw our most practically exciting results with language models. So we got pretty significant compute efficiency multipliers. So a compute multiplier lambda means with C training flops, it achieves the same loss as a dense model with lambda C training flops. So you're basically dividing your computation by lambda for what you would have expended if you were using a non-MOE model. And so the BTT MOE worked a fair bit better than non-MOE and also a bit better than standard MOE. We're now really considering a lot of these questions for attention specifically. So in the results I showed, we're replacing all of the linear layers with structure, including the projection matrices in attention. So this mixtures of experts, for example, that I'm talking about here is considering attention, but we weren't considering like attention really separately. We were just looking at, all of the dense matrices and replacing them with structured matrices, and that included the attention projection matrices. Right now, we're actually thinking a lot specifically about what sort of structure we might want to use to represent attention. And so this is just a very quick sneak peek. Quite often, attention is represented with some sort of low rank structure. We're looking at like bilinear structure, at bilinear block tensor trains. We're trying to understand how assumptions around locality might actually affect structure that's not currently being considered in the way attention is represented, and how this might sort of impact performance on all sorts of other downstream tasks. There are, in general, a lot of open questions associated with this research agenda. So, why did the block tensor train end up being the best structure that we considered in all of the domains that we looked at, like vision, language, tabular data regression, et cetera, and across the models we considered MLPs, VITs, LLMs, et cetera. This wasn't something I necessarily expected. I thought, well, since the structure that works well is tightly corresponding to certain modeling assumptions, then we might expect different structures to be good in different modalities because presumably we want to be making different assumptions for those modalities. Turns out it just hasn't been the case empirically. And so possibly the BTT is capturing assumptions that are just relevant to each of those modalities. They're relatively universal assumptions. At the same time, I would really be excited to see this pursued a bit further to understand, well, can we actually do better if we're really specifically considering a particular problem and domain and really coming to grips with the assumptions that should be helpful in that domain? Also, there's this question of how structure interacts with architecture. So there are all sorts of architectural formulations like densely connected neural nets that might be much more amenable to aggressively structured representations. Of course, there's this question of how you can explore structure in your own projects, and that extends beyond making transformers more efficient. It's really this broad research agenda, and I'd really love if you could check out COLA and let us know, how it works for your project, and give us any feedback on the repo, even if you hate it. Just say like, this really has been frustrating for me, and here's why, and then we'll try to work with you to see if we can make it better. We haven't had that much of that sort of feedback. The people who've used it seem to have benefited a lot from it, and it's really a backbone now for GP JAX. It supports both JAX and PyTorch. But if you tried and it doesn't work, we would really love to hear from you.
I just got an email saying that here's a code you wanted to access your Microsoft account, and here's a code.
Yeah, sure. Do you want to ask a
I
question?
didn't do anything. I mean, just 2 minutes ago, 3 minutes ago.
Okay. Sorry, I think
Maybe the mute
yeah,
was on or
sure.
something.
I muted him by mistake.
I thought that was a question. I was getting very
what
scared. I
did-
didn't know the answer.
Yeah,
What did
let
you
me see
do?
if I can mute him.
I was trying to
Yes,
update the office and log in and so on.
let me unmute Andrew now.
Okay.
Yeah.
Should we
Is it
proceed?
can you hear me, Andrew?
I hear you. Can you hear me?
Yeah.
Great.
Good.
Okay, so no worry. I was saying, yeah, I don't know if I was muted at that point, but I thought that person was asking me a question. I was like, I don't know anything about Microsoft Teams. Okay, I won't take too much longer. I want to leave a bit of time for questions, but I just want to end with a philosophical aside around how we should really represent our inductive biases. I think in the learning theory community and maybe the mainstream machine learning community, most people think about inductive biases as restriction biases, kind of like in that convolutional neural net example where we restrict the size of our hypothesis space. And as a consequence, our model will be more quickly informed by data and will achieve good generalization. I actually prefer thinking of inductive biases as soft inductive biases. I think this is natural from a Bayesian perspective, but it's not really the way that the community generally thinks about inductive biases. So instead of having hard architectural constraints, for example, just embrace a flexible hypothesis space and have a soft preference for certain solutions over others. And so that's what I'm depicting in this conceptualization here, where we might start with some restriction bias and then think about like what other solutions we might want to represent, but we might want like less of a prior preference, for instance, for those types of solutions. And so they're represented in lighter blue there. And we have an instantiation of this philosophy when it comes to equivariances in something called residual pathway priors. So in Bayesian deep learning, there's often this question of like whether we can have more informative priors for our model parameters. And this is one way of achieving that in certain settings. And so the residual pathway prior puts a distribution over your neural network parameters that has a covariance matrix that lives in some equivariant subspace plus some orthogonal complement. So it says like, we want to prefer structures that are equivariant or close to equivariant in some way, but we're not going to rule out other solutions. And this encapsulates actually a more general principle. The reason it's called residual pathway priors is because it combines this sort of restrictive layer with strong inductive biases and constrained solutions with a more flexible layer that's trying to be used to explain anything that's left over that can't be explained by the structured layer. And so this kind of allows you to have evolving complexity as needed to describe the data. And what we found actually that was kind of surprising to me, maybe less now with hindsight, but it was at the time, was that this approach often would work as well as a model that had been perfectly constrained in a particular setting. So if we're modeling molecules, for example, we know we have rotation invariance, but actually, if we use this residual pathway prior with approximate rotation equivariance, it would just very quickly contract to exact rotation invariance and be as good as like an exactly constrained model. In settings where you didn't really have any of these types of constraints, it would be quite competitive with a model that wasn't using one of these priors and didn't have any specific constraints. And then if you were anywhere in between, it would work a lot better. And so I started to see this as really a principle for how we should think about constructing intelligent systems. Here I have another visualization of what happens during training, and there'll be kind of a bit more on this coming out shortly. So this is really just a sneak preview. You're all seeing this for the first time. Here, basically, we're looking at what happens when we train a model through standard optimization with biases specified in various different ways. So on the left, we have a flexible hypothesis space, but really a uniform bias over the different solutions. Quite often in those instances, we'll just find a solution that overfits. It achieves low training loss, but it doesn't generalize very well. In the middle panel, we have soft biases for certain solutions over others, but also a fairly flexible hypothesis space. Here we're guided towards solutions that might generalize better. In the right panel, we have a restriction bias. So we really constrain our hypothesis space, but as a consequence, we typically won't find solutions that will work as well as in the middle panel because we're being too conservative. What tends to work better is having a flexible hypothesis space and then having certain preferences for certain types of solutions. And we can instantiate this idea with very, very simple examples. So for example, if we have just a higher order polynomial and we penalize the higher order coefficients more than the lower order coefficients, the model will try to explain the data as much as possible with the low order terms, and then anything that's kind of left over with the higher order terms. So if you see data and you're doing regression that appears to kind of basically fit on a straight line, it'll want to use the straight line to fit that data, even if it's like a trillionth order polynomial. And then if you start to see structure that deviates from that, it will start to use the higher order coefficients as needed. And these kinds of models are very good in a variety of different regimes and for a variety of different data sizes. So there's this philosophical question about whether we should use a different model if we have like a different size training set. Like if I have 5 training data points, should I use a different model than if I have 5 million training points? And I think most people would say yes. I think philosophically the answer is no. And if we use these kinds of procedures, we can see that we get competitive performance with constrained models for small data sizes, with unconstrained models for large data sizes, and good performance also in quite a variety of different settings. And this isn't just an intuition, it's actually consistent with rigorous frameworks for formalizing generalization like Pac-Bayes and even the simpler finite hypothesis bounds. So here I have just the basic finite hypothesis bound with a prior, and it's saying that empirical risk, expected risk is upper bounded by empirical risk on our training set, plus this term which involves this kind of complexity penalty, this log 1 over pH, which is p is a prior over hypotheses, and delta is the probability that we want this guarantee to hold for. And so what this kind of says in words is like we want a flexible model that is going to be able to fit the data because that's going to give us a better upper bound on generalization. But we also want a prior that might favor certain types of solutions over others. And we can push this even further by considering particular priors like the Solomonov prior. And this allows us to convert this finite hypothesis bound into having a complexity that depends on something called Kolmogorov complexity, which we can then upper bound through the stored file size of our model. And so what this is saying is embrace a flexible hypothesis space, in combination with a compression bias. And in some cases, larger models actually have a stronger compression bias, and that's why they're achieving better generalization. It's not maybe primarily because they're more flexible. It's also because, they have a stronger bias for compression, and this explains things like double descent, benign overfitting, etc. All of those generalization phenomena are actually completely consistent with this sort of theory used to describe generalization. And the assumptions are actually relatively mild. Like, you might wonder, oh, well, does the model actually have to use that prior or something? The answer is no. Like, you just need to train your model, record its empirical risk on the training set, record like how much memory it takes to store that trained model, and you have an upper bound on generalization for that model. Of course, the bound is like assuming that you're applying it to data drawn from the same distribution it's been trained on and so on. Like, there are assumptions, but like they're relatively mild. It's not like you need to make some wildly unrealistic assumption. You are getting bounds for the models that we're working with. And you can actually develop these bounds for models that have millions or even billions of parameters by embracing this compression perspective. And so here we just have this visualization of how the bound compartmentalizes into compression and empirical risk to get a bound in purple on the left. And we see that these are non-vacuous bounds. They're better than random guessing. And they often also tend to get better as the models get larger. So this does very much actually track the behavior that we see empirically. And this is different from other generalization frameworks like Rademacher complexity and VC dimension, which are really concerned with the size of the hypothesis space. So like Rademacher complexity basically measures whether you can fit +1, -1 uniform random noise. And so if you have a very flexible model, it'll have bad Rademacher complexity, and there'll be no good generalization guarantees under that formalism. But with Pac-Bayes and finite hypothesis bounds, you can have actually pretty tight guarantees on these kinds of very flexible models. And I think this is sort of quite complementary to this perspective of soft inductive biases versus restriction biases. And they apply actually quite generally. Like, there are a lot of misconceptions about Pac-Bayes, I would say. In addition to the assumptions, I think, being relatively mild, like they have assumptions, but they're not particularly restrictive. You can also get these frameworks to apply for deterministically trained models. Like, I think a common misconception about Pac-Bayes is like, well, this is a stochastic network, like a Bayesian neural network or something, and we're just looking at the expected risk of a single posterior sample. But like, you can actually consider point mass posteriors. It doesn't need to be the Bayes posterior, and you can derive these finite hypothesis bounds with just something like a Solomonov prior, and like this applies literally to the models that we're just training in a usual way. And so this is something I'm very excited about, and generally I'm very optimistic about the role of theory in deep learning. All right, thank you. That's everything.
Cool. Yeah, thanks, Andrew. I think we have time for some quick questions. If anyone wants to ask anything, please write something in the chat. There is already one question there. I also want to ask one. So you have talked about this parameterization in terms of this BTT representation. And one thing that is clear is that you can get computational gains from that. And I was wondering if you could say something about memory. Are there any memory savings also because of this, in terms of maybe the parameters that you may need to store and all that?
It's a really great question. And this is something I'm actually excited to explore further. I think that in pre-training, we're mostly compute bound. At test time, we're actually more memory bound. And I think that these kinds of structures actually could probably help even more with memory than they help with compute. And that's just not something that we've explored very much. We've looked mostly just at compute performance as a function of flops. There is, I think, a related consideration around like performance as a function of wall clock time. And so I would say with VITs, we do see improvements. With LLMs, it depends. I think the MOE can lead to wall clock time improvements. It's not, for me, and I think many people right now, the quantity of primary interest, because wall clock time depends so much on implementation and specific hardware. And right now, we're very interested in prototyping ideas more than implementations. And once we know that something has better scaling behavior in terms of flops, and we're very excited to use that structure, we can come up with some CUDA implementation that will be parallelized, et cetera, and we'll have good wall clock time. But I think wall clock time can also be bounded by like memory and flops. And so I think, yeah, this is sort of an exciting direction. We haven't thought about it much, except to have the intuition that like we're probably more compute bound in pre-training and more memory bound at test time. And I actually think the story could be even more favorable to structure if we're thinking about memory.
Mhm. Good. There is one question in the chat. I don't know if you can see that, Andrew. It says, while full rank ensures better scaling laws, does it
Mhm.
also improve generalization performance across tasks, or are there diminishing returns in certain domains?
Mhm. So I think that these observations do apply across various different tasks. Intuitively, I might actually expect more constrained structures to be more task specific than the less constrained structures. So I think like actually like if we're really concerned about cross-task performance, we might even expect some of these results to be stronger because they're less constrained, so they're not kind of making assumptions that might not clearly apply to a bunch of other tasks.
Mhm. Good. We are actually out of time. So I see, yeah, if there are not many questions, I would just say thank you, Andrew. Thanks a lot for having you here. I think the presentation has been great. I'm super curious to try this BTT parameterization and see where this, how useful it can be. But yeah, it looks super promising to me. Great. Thanks, and see you soon.
Thanks so
Hopefully in
much for having
Cambridge
me. Yeah, hopefully I'll see you in the summer.
in the
It's
summer.
yeah, really great being here. Yeah, thank you.
Good. Bye. Bye. Bye.
Thanks. See you. Bye bye.